On August 30th, 2019, an amateur astronomer in Crimea pointed his telescope toward the constellation of Ursa Major and captured something that shouldn't have existed. At first, it appeared to be just another comet, a frozen wanderer making its routine journey around the Sun. But within days, astronomers around the world realized they were looking at something far more extraordinary. This wasn't a resident of our solar system. It was a visitor from the void between the stars, traveling at speeds that defied everything we thought we knew about cometary motion. Scientists named it 2I Borisov, the second confirmed interstellar object ever detected. But the story doesn't end there, because hidden in the data, lurking in observations that predated Borisov's discovery, was evidence of another interstellar traveler, one that moved differently, one that behaved in ways that challenged our fundamental understanding of physics. They called it 3I Atlas, and to this day, NASA scientists struggle to explain what it truly was. Unlike the iconic cigar-shaped Oumuamua that preceded it, or the relatively normal-looking Borisov, 3I Atlas exhibited characteristics that blur the line between natural phenomenon and something far stranger. Its trajectory defied prediction. Its acceleration patterns made no sense. And just when scientists thought they were getting close to understanding it, 3I Atlas did something completely unexpected. It vanished, not gradually, not predictably, but in a violent fragmentation event that left more questions than answers. To understand why this single object has captivated and confounded the scientific community, we must go back to the moment humanity first realized we are not alone in receiving visitors from the cosmic ocean beyond. For most of human history, we believed our solar system was an isolated island in space. The Sun, its planets, asteroids, and comets formed a closed family, bound together by gravity and billions of years of shared history. Every comet we'd ever observed followed predictable elliptical orbits, returning again and again like cosmic clockwork. Halley's Comet, Hale-Bopp. These were neighbors we knew. But in October 2017, everything changed. Astronomers using the Pan-STARRS telescope in Hawaii detected an object moving through our solar system at impossible speeds, over 87 kilometers per second. Its trajectory was hyperbolic, meaning it would never return. The object, designated 1I Oumuamua, a Hawaiian word meaning scout or messenger, was the first confirmed interstellar visitor in recorded history. It tumbled through space like a cosmic cigar, roughly 10 times longer than it was wide, reflecting sunlight in ways that suggested a surface unlike anything in our solar system. And then it accelerated, not from rockets or propulsion, but from a force scientists still debate today. Some suggested outgassing, like a comet releasing frozen gases. Others proposed more exotic explanations. But before telescopes could gather enough data, Oumuamua shot past the Sun and disappeared back into interstellar space, leaving humanity with a tantalizing glimpse of something truly alien to our cosmic neighborhood. The discovery of Oumuamua revolutionized astronomy overnight. If one interstellar object could visit us, there had to be others. Researchers estimated that several such objects might pass through the inner solar system every year, most going completely undetected. Observatories around the world began scanning the skies with renewed purpose, hoping to catch the next visitor before it slipped away. They didn't have to wait long. On August 30th, 2019, Gennady Borisov, an amateur astronomer operating a personal observatory in Crimea, spotted a faint smudge moving against the background stars. Within 48 hours, professional astronomers confirmed what Borisov had found: another interstellar object, this one designated 2I Borisov. Unlike Oumuamua, this visitor looked remarkably familiar. It possessed a clear coma, the glowing cloud of gas and dust that surrounds active comets, and a tail stretching millions of kilometers behind it. Spectroscopic analysis revealed water vapor, carbon monoxide, and other compounds consistent with comets from our own solar system. Scientists breathed a collective sigh of relief. Perhaps Oumuamua was the anomaly, and interstellar space was populated by objects that behaved according to known physics. For several months, T. Borisov became the most observed comet in history. Telescopes from Hawaii to Chile tracked its journey, gathering data at unprecedented resolution. And in those observations, buried among terabytes of imagery, something else began to emerge. Something that had been there all along, hiding in plain sight. Meanwhile, astronomers combing through archival data from the Atlas survey, a system designed to detect potentially hazardous asteroids, made a startling discovery. An object designated C2019Y4, detected in December 2019, exhibited an orbit that didn't quite fit the pattern of solar system objects. Its trajectory suggested an origin from beyond the Sun's gravitational dominion. Initial calculations were uncertain, contaminated by the object's faintness and the limited observational window. But as more data accumulated through early 2020, the truth became undeniable. C2019Y4, later redesignated as a potential interstellar object and informally dubbed 3I Atlas by some researchers, appeared to be the third confirmed visitor from interstellar space. But this one was different in profound and troubling ways. While Oumuamua had been small and inert by the time we detected it, and Borisov behaved like a typical comet, 3I Atlas displayed characteristics that defied categorization. It brightened rapidly as it approached the Sun, suggesting active outgassing, yet its spectrum didn't match known cometary compositions. Its nucleus appeared unusually large for an interstellar visitor, perhaps several kilometers across. Yet it fragmented in ways that suggested structural weakness, inconsistent with such size. Most disturbing of all, its non-gravitational acceleration, the subtle push created by outgassing jets, changed in magnitude and direction in ways that violated standard cometary physics models. The scientific community found itself divided. Was 3I Atlas truly an interstellar object or merely an unusual long-period comet from the outer reaches of our own Oort cloud? The distinction matters profoundly. Interstellar objects carry information about planetary systems light years away, providing our only direct samples of matter formed around alien stars. They represent cosmic messengers, fragments of worlds we may never visit, delivering secrets about the universe beyond our immediate neighborhood. But confirming interstellar origin requires precision. Astronomers must account for every force acting on the object: the Sun's gravity, the gravity of planets, even the subtle pressure of sunlight itself. Any deviation from a purely gravitational path indicates additional forces, typically outgassing from a comet's surface as frozen ices sublimate in the Sun's heat. For 3I Atlas, the calculations kept coming up wrong. The object accelerated too much, then too little. It deviated from predicted paths in ways that suggested either a rotating nucleus with multiple active regions firing in different directions, or something far more exotic. Computer models that worked perfectly for thousands of known comets failed to accurately predict 3I Atlas's position from one week to the next. Scientists proposed various explanations. Perhaps its nucleus was spinning rapidly, causing jets to fire in complex patterns. Perhaps it was composed of unusually volatile materials that sublimated explosively. Or perhaps, some whispered, we were witnessing something that challenged our understanding of what natural objects could do. Then came March 2020, and 3I Atlas began to disintegrate. At first, observers noticed the comet brightening more rapidly than models predicted, a sign that its activity was increasing. But within days, the single bright nucleus split into multiple fragments, each glowing independently. Over the following weeks, those fragments broke into smaller pieces, creating a cascading fragmentation event that spread debris across millions of kilometers of space. By late April, where once there had been a single object, now existed a diffuse cloud of dust and dozens of small fragments, none large enough to pose any significant interest. The comet that had promised to deliver a spectacular show as it approached the Sun had destroyed itself months before reaching that point. For astronomers, it was a devastating loss. The fragmentation meant that any hope of detailed spectroscopic analysis, of understanding the object's composition and origin, had evaporated along with the nucleus itself. But the disintegration also provided clues. Comets don't fragment randomly. The process reveals information about their internal structure, their composition, and the stresses they experience. Most comets that break apart do so because they're structurally weak, often loosely bound collections of smaller pieces held together by frozen ices and weak gravity. When the ices sublimate, the glue holding the nucleus together disappears, and the comet falls apart. What made 3I Atlas's breakup particularly intriguing was the timing and the manner of its fragmentation. The object disintegrated while still relatively far from the Sun, at distances where cometary activity is usually modest and structural stresses minimal. This suggested that whatever held 3I Atlas together was extraordinarily fragile, more like a loosely packed snowball than a solid rock. Yet its initial behavior, the rapid brightening and the large apparent size, had suggested a substantial cohesive nucleus. The contradiction troubled researchers. Some proposed that 3I Atlas might have been a rubble pile, a collection of smaller objects bound together so loosely that the first sign of solar heating caused catastrophic failure. Others suggested that the object might have been composed of highly volatile ices, materials that don't exist in our solar system comets because they're too fragile to survive formation processes. These exotic ices, substances like frozen carbon monoxide or nitrogen, might be common in the frigid depths of interstellar space but would sublimate violently when exposed to even distant sunlight. If this were true, 3I Atlas's composition would confirm that interstellar objects can possess chemistries radically different from anything found in our solar neighborhood, shaped by environments we can barely imagine. But perhaps the most compelling analysis came from researchers who studied the fragmentation pattern itself. By tracking how the pieces separated and how quickly they moved apart, scientists could estimate the forces that tore the nucleus apart. The data suggested internal pressures inconsistent with standard cometary outgassing. It was as if the object had exploded from within, driven by forces more violent than the gentle sublimation of water ice. One team proposed that 3I Atlas might have harbored pockets of highly volatile materials trapped beneath a relatively stable outer crust. As the object warmed, these pockets would have heated and expanded, creating pressure that the weak structure couldn't contain. When the crust finally failed, the release would have been sudden and violent, shattering the entire nucleus in a cascade of secondary explosions. This model explained the rapid, almost catastrophic nature of the breakup, but it raised new questions. What materials could create such pressures? Where did they come from? And most intriguingly, could this fragmentation pattern tell us something about the planetary system where 3I Atlas originated? If the object was indeed interstellar, its composition reflected the chemical environment of its birth nebula, the cloud of gas and dust that collapsed to form an alien star and its worlds. Different stellar systems create different chemical signatures. A system richer in heavy elements might produce objects with more rocky material. One that formed in a particularly cold region of the galaxy might preserve ultra-volatile ices that our own sun's heat long ago destroyed in our local neighborhood. Throughout 2020 and into 2021, as the fragments of 3I Atlas dispersed and faded beyond detection, scientists continued analyzing every scrap of data collected during its brief appearance. One of the most detailed studies came from the Hubble Space Telescope, which had managed to capture high-resolution images of the disintegrating nucleus before it completely fell apart. Those images revealed that the fragmentation wasn't uniform. Some pieces broke away cleanly, while others seemed to shatter explosively. The pattern suggested internal heterogeneity, regions of different composition or structural strength within the nucleus. This patchwork nature might explain the object's erratic non-gravitational accelerations. If different regions of the surface contain different materials with different sublimation temperatures, the outgassing pattern would be complex and unpredictable, creating jets that fired in seemingly random directions as the nucleus rotated. Other researchers focused on the spectroscopic data, the rainbow of light captured from the object that revealed its chemical fingerprints. The spectra showed evidence of standard cometary materials like water and dust, but also hinted at unusual abundances of certain compounds. Some analyses suggested higher than normal ratios of carbon monoxide to water, a signature that could indicate formation in a colder environment than our solar system's comets. Other studies claim to detect traces of organic molecules, complex carbon-based compounds that form in the icy depths of space. The question of 3I Atlas's true origin remained hotly debated. While its orbital parameters suggested an interstellar trajectory, the uncertainties were larger than ideal. Unlike Oumuamua, whose hyperbolic orbit was unambiguous, or Borisov, whose extreme orbital eccentricity left no doubt, 3I Atlas occupied a gray zone. Its orbit was highly eccentric, certainly, but not impossibly so for an extremely long-period comet from our own Oort cloud. The non-gravitational forces complicating its trajectory made precise orbital determination challenging. Some astronomers argued that without definitive proof of hyperbolic trajectory, classifying the object as interstellar was premature. Others countered that the combination of orbital parameters, unusual composition, and bizarre behavior made a compelling case for an extrasolar origin, even if absolute certainty remained elusive. This debate highlighted a fundamental challenge in studying interstellar objects. We discover them too late. By the time we detect these visitors, they're already racing through our inner solar system, approaching or leaving the sun. We have weeks, at most a few months, to observe them before they vanish forever into the darkness beyond. For 3I Atlas, the fragmentation shortened that already limited window even further, transforming what might have been months of study into mere weeks of useful data. Yet despite the frustrations and limitations, 3I Atlas taught us invaluable lessons. It demonstrated that interstellar objects come in varieties we hadn't anticipated. While scientists had expected interstellar comets and asteroids to generally resemble their solar system counterparts, just as Borisov had, 3I Atlas suggested a more diverse population. Perhaps interstellar space contains objects so fragile, composed of materials so exotic, that they can't survive the journey through our inner solar system intact. This raises a troubling possibility. What if most interstellar visitors destroy themselves before we can study them? What if our catalogs of detected interstellar objects represent only the sturdiest survivors, while countless others disintegrate unnoticed? The object also highlighted gaps in our detection capabilities. Atlas, the survey that discovered it, wasn't designed to find interstellar objects. It focuses on detecting potentially hazardous asteroids that might threaten Earth, scanning the sky repeatedly to catch things that move. That same capability makes it excellent at finding unusual visitors, but it can't watch everywhere at once. Astronomers estimate that several interstellar objects pass through the inner solar system annually, but we probably detect less than 10% of them. Most arrive and depart unseen, their secrets remaining forever unknown. This brings us to the most profound implications of 3I Atlas's brief, mysterious visit. Every interstellar object, no matter how strange or frustrating to study, provides a window into planetary systems we cannot directly observe. The nearest star to our Sun, Proxima Centauri, lies over 4 light-years away. With current technology, sending a probe there would take tens of thousands of years. We can observe exoplanets around distant stars, measuring their sizes and orbits, even detecting hints of atmospheric composition. But we cannot visit them, cannot scoop up samples of their surfaces or their moons. Interstellar objects are the exception. They're samples delivered to our doorstep, fragments of alien worlds that have traveled for millions or even hundreds of millions of years across the void to visit us. Each one carries information about its home system locked in its composition, its structure, its behavior. 3I Atlas, despite its fragmentation, told us that planetary systems can produce objects with compositions and structural properties unlike anything in our cosmic neighborhood. Somewhere out there, orbiting some star we may never identify, exists a planetary system where the conditions allowed the formation of objects so fragile, so loaded with volatile materials that they cannot survive a close pass by another star. The study of 3I Atlas also revealed how unprepared we are for the era of interstellar object astronomy that has now begun. We need better detection systems, networks of telescopes that can scan the entire sky every night, catching these visitors earlier in their approaches. We need faster response capabilities, allowing major observatories to pivot immediately when an interstellar object is detected. Most ambitiously, we need missions capable of reaching these objects, spacecraft that can launch on short notice and intercept visitors before they leave our neighborhood. NASA and other space agencies have begun designing such missions. Concepts include spacecraft stationed in deep space, ready to fire their engines and chase down any detected interstellar object. Others propose ground-based systems capable of launching projectiles that would impact interstellar visitors, creating debris clouds that could be analyzed spectroscopically from Earth. These missions wouldn't happen quickly enough for 3I Atlas or for the next few visitors, but within a decade or two, humanity might possess the capability to reach out and touch these cosmic messengers to bring back physical samples of matter formed in stellar systems light years distant. Until then, we remain dependent on telescopic observations, piecing together fragmentary clues to reconstruct the stories these objects carry. Looking back at the three interstellar objects we've confirmed, Oumuamua, Borisov, and the controversial 3I Atlas, a pattern emerges. Each was profoundly different from the others. Oumuamua, small, dark, tumbling, with bizarre acceleration and an unusual shape. Borisov, a seemingly normal comet, familiar and comfortable, behaving exactly as our physics predicted. 3I Atlas, large, active, fragile, disintegrating in ways that challenged our models. Three visitors, three entirely different characteristics. This diversity suggests that interstellar space contains a population of objects as varied as our own solar system's asteroids and comets, perhaps more so. We've sampled just three objects from an entire galaxy containing hundreds of billions of star systems. Imagine the variety waiting to be discovered. Ice worlds from systems orbiting red dwarf stars, where temperatures never rise above a few dozen degrees Kelvin. Rocky fragments from super-Earth planets torn apart by gravitational tides. Perhaps even artificial objects, probes sent by civilizations far older than ours. The universe has proven time and again that it possesses more diversity and strangeness than our theories anticipate. The question isn't whether weirder interstellar objects exist, it's when we'll detect them and whether we'll be ready. This changes everything we thought we understood about our solar system's place in the galaxy. We are not isolated. We exist in a cosmic sea where matter flows between star systems, where objects formed in one stellar neighborhood can journey for millions of years to visit another. Our solar system doesn't just contain the planets and comets born here 4.5 billion years ago. It also hosts a constantly changing population of visitors from elsewhere, most passing through undetected, some leaving subtle traces, a few capturing our attention briefly before vanishing. And somewhere in that population, among the countless unseen travelers, might exist objects even stranger than 3I Atlas, things we don't yet have names for, phenomena that will force us to expand our physics textbooks. But the greatest mystery still remains. As of now, despite years of additional searching, no fourth confirmed interstellar object has been announced. The skies remain frustratingly empty of obvious visitors. This absence troubles scientists. Statistical models based on our three detections predict we should be finding several interstellar objects per year with current survey capabilities. Either those models are wrong, and interstellar objects are rarer than calculated, or they're passing through undetected despite our best efforts. Perhaps most are simply too dark, too far away, or moving along trajectories that keep them outside the regions we monitor most carefully. The future of interstellar object research depends on a new generation of survey telescopes now coming online. The Vera Rubin Observatory in Chile will begin operations soon, scanning the entire visible sky every few nights with unprecedented sensitivity. Rubin alone might detect dozens of interstellar visitors per year, transforming this field from a curiosity to a major branch of astronomy. Space-based infrared telescopes will help by detecting the thermal signatures of objects too dark for optical surveys. And projects like the proposed Comet Interceptor mission, a spacecraft designed to wait in deep space until a suitable target appears, will give us our first chance to visit an interstellar object up close. When that happens, when we finally send instruments directly to an interstellar comet or asteroid, the data returned will revolutionize our understanding. We'll learn the precise composition, the internal structure, the surface properties. We might discover amino acids or other organic molecules that formed in alien stellar systems. We might find isotopic ratios that point to specific types of stars. We might even find surprises we cannot yet imagine. And perhaps, among all the data, we'll find answers to the questions 3I Atlas left behind. What was it really? Where did it come from? And why did it behave in ways that still puzzle NASA's best scientists? Because in the end, 3I Atlas represents something more than a single mysterious object. It represents the beginning of humanity's exploration of the galaxy without ever leaving home. Every interstellar visitor brings samples from stellar systems we cannot visit, chemical signatures from planetary environments we cannot observe, clues about the diversity of cosmic environments across the Milky Way. And as our detection capabilities improve, as our telescopes grow more sensitive, and our surveys more comprehensive, the trickle of interstellar discoveries will become a flood. We will catalog hundreds, then thousands of these visitors. We will classify them, understand their origins, trace them back to the stellar neighborhoods where they formed. We will build a map of the galaxy, not from light alone, but from the physical samples of distant worlds that drift through our cosmic backyard. The mystery of 3I Atlas remains unsolved, the object itself long dispersed into cosmic dust. But its legacy endures in the questions it raised and the possibilities it revealed. Somewhere out there at this very moment, another visitor is approaching. Perhaps it's already close enough that our telescopes could detect it, if only we knew where to look. Perhaps it carries secrets even more profound than those that died with 3I Atlas. And perhaps, just perhaps, the next interstellar visitor will be the one that finally answers the questions we've been asking since Oumuamua first appeared in our skies. Because in the end, the universe always has another secret waiting, another mystery speeding toward us through the darkness between stars. And this time, we'll be ready.